Hello everybody, Adam Lusek here, and today we're going to be talking about language model alignment, or pretty much all the stuff that happens after you pre-train your base language model and getting it to align more to your expected outputs and values. We'll be going over what the alignment stage of language model training is, and also a little bit of how to do it yourself here. So covering pretty much everything that modern day AI labs are using to tune and guide their language models. So to understand at a deeper level how alignment and fine-tuning works, we have to really look at the total development lifecycle of a language model, starting with, of course, the pre-training for the base model. Pre-training is the step where the base language model is actually learning all of the representations of our human language in its neural network. So this is where it starts to pick up on the patterns, relationships, and contextual representations of words being trained on this large corpus of text. This is usually done by training the base model to predict parts of input from other parts of text, similar to a few of these examples here in this pre-training objectives diagram. And this is really where our first steps of modeling language and then being able to generate realistic sounding or looking language starts. But just having a model that can relatively understand the features of text and start to generate a little bit of text itself isn't so useful unless we actually specify what we want it to do, which is where the alignment stage comes in, starting with supervised fine-tuning. The big one-liner about supervised fine-tuning, or SFT, is that it bridges the gap between general language modeling, which is what our pre-trained language model is meant to do, and actual task-specific performance. During supervised fine-tuning is usually when we are adapting this pre-trained model for different specific capabilities. This can be things like handling structured tasks or specific formats, like taking our base language model and then instruction tuning it so that it can follow question and answer flows or chat flows. And then also this is where we can start to instill a little bit of our specific domain knowledge into. This is usually what most people think about when they think about fine-tuning language models and taking whatever their domain-specific data or domain knowledge and then instilling it a little bit more into our base language model. Usually, these base language models have already undergone some form of supervised fine-tuning from the AI labs that they are being made from, whether it's just to bolster the language model with additional information, or for specific things, like I was saying, with chat-based or term-based conversational flows. But supervised fine-tuning is only one step of the alignment phase. The other half is actually making sure that our models are behaving in accordance with human values or specific preferences. And this is where a lot of different techniques come in to really optimize for human preferences by learning what humans consider to actually be good and bad responses, and then iterating on your model to actually go more towards generating good responses. And then we can also do some things here like matching human values by incorporating ethical considerations or social norms, and then maintaining consistency across different contexts or being able to reliably generate between different types of interactions. This is usually done through different reinforcement learning techniques and is considered almost the last mile of refining a language model's output. So in this stage, you're really more tuning your language model towards getting those good quality responses that you expect. This is usually done through, and we'll get into this in a little bit, data that's labeled by humans. So next time you see something like a thumbs up or a thumbs down on ChatGPT or Claude, what they're doing is taking that information of whether you say one response is better or worse, and then being able to use that data to actually train their model to more reliably generate responses that we actually prefer or find useful. So to dig in a little bit deeper into the entire development lifecycle, we're going to start with one level down into supervised fine-tuning. And supervised fine-tuning can kind of be thought of as adapting language models to really domain-specific or capability-specific knowledge. The process that this follows is that usually you identify your target domain or capability, defining the specific use case, skill, or domain that we want to enhance the model's performance at. For our little graphical example, I'm going to choose healthcare here. And so now that we've got healthcare, what you need to do is actually then design strategic prompt templates that create a diverse set of prompts that comprehensively cover your intended domain interactions or scenarios. So all of these prompts are all related to the healthcare industry. Then with these prompts, we want to generate some very quality data of what we expect the language model to start learning from and replicating. So this is where we really start to generate these expert demonstrations based on the prompts. Usually this is done through domain experts or having humans literally write all of these things together, and that's usually the best quality data. Some work is being done to actually create synthetic data using language models to do this step, and we're getting some pretty good results. So maybe I'll cover that a little in the future. But then having our high quality data set of expected prompts and then expert created responses, we can then use this data set to do our further alignment and fine tuning towards this domain or capability. So in this sense, we are using this data to train a language model to be more resilient or robust in using healthcare data or generating healthcare specific responses, which is exactly what the creator of this healthcare data set did. Created a model and fine-tuned a language model, the pre-trained model on the curated data set using supervised learning to adapt its behavior to the target domain. And so while this can effectively instill the ability to learn these different capabilities or domains into our base language model, there's still one major issue that's actually been identified during this step. And that's during supervised fine-tuning, while we only train on the chosen or preferred responses that we've created in the dataset, the model's likelihood of generating both chosen and also rejected responses increases similarly over these training steps. This essentially means that while it will get better at creating, per se, healthcare-related responses, the actual quality of those responses and whether they're good or bad doesn't necessarily get differentiated here during the supervised fine-tuning stage. And this happens a little bit more specifically because the base model here is actually learning to generate responses that are similar to the human answers without actually doing any explicit distinguishing between preferred and non-preferred content. So supervised fine-tuning improves our general task completion, but doesn't explicitly discourage any unwanted or low-quality responses. A more technical way of saying this is that the generation of the language model and its semantic space of actual possible responses remains very broad, as supervised fine-tuning only provides these positive examples that we're training on. So to mitigate this, our final step of doing some sort of preference alignment is then applied, where the LLM will then explicitly learn to actually differentiate between these chosen and rejected or preferred and non-preferred responses. Which brings us to our preference alignment stage, or being able to actually encourage preferred response generation from our language model. The first and earliest kind of form of this that AI labs have started to apply is actually what's called reinforcement learning from human feedback. And so this is where we're actually going to align a model's outputs with human preferences through iterative feedback and optimization using reinforcement learning techniques. If you're unfamiliar with different reinforcement learning techniques and how it kind of works, I'll have a video pop up right now of a video I just made recently going over all sorts of different reinforcement learning capabilities and approaches and how to actually apply them so that you can better understand what's going on in this process. But what's happening when we're doing reinforcement learning for preference tuning here and preference alignment is we're first going to take our fine-tuned model that's gone under supervised fine-tuning and generate a diverse set of responses for individual prompts. So taking the same prompt, we're going to create multiple different iterations of generations from our model. This is then where the human feedback is actually going to come into this. So we then have humans actually rank or compare their preferences towards the different response options that the model generated. We then use these labeled data from human feedback to create a second model, a reward model that can actually accurately predict human preferences. So essentially, we're going to have our base model. We're going to take one prompt, generate multiple answers, ask someone which answers they prefer, and then if we have enough of those data points of what these humans prefer, we can actually then create a reward model that can accurately predict then from a language model's generation the likely estimate of human preference. This then kicks off the standard reinforcement learning kind of training loop where the language model will generate a response. Our reward model that we were able to create will provide a reward that encourages generations that are in alignment with the human preferences that it was actually trained on. And in staying true to reinforcement learning, the weights will all be updated to try and maximize this reward, thus aligning our preferences more towards our expected human preferences. And so as I was saying a little bit earlier, some of the sneaky ways that people like OpenAI or Anthropic actually start to collect this human preference data is by showing you, maybe ChatGPT really likes to do this, is every once in a while you'll ask a question and it'll give you two responses that you have to choose. And this literally just says, which response do you prefer? And so they'll be using this data to help figure out these preferences and create these data sets. Similarly to things like Anthropic Claude, you'll see a thumbs up or thumbs down, and you can provide explicit feedback about why you liked or didn't like a response. They even then say here that when you submit the feedback and provide permission, they use this for training and improving their models. So, bit of a good way of crowdsourcing this generally tedious to gather data. And so while RLHF has managed to give some really good results, one of the things that you can see here is that it takes a lot of steps. You need to create a second reward model and do all sorts of reinforcement learning techniques that can kind of complicate and destabilize things during the training processes here. So there have been, of course, some evolutions of this process to make it a little bit more streamlined and simple. And so the next step up from RLHF is actually called DPO, or Direct Preference Optimization. And DPO takes inspiration from the RLHF process, but the researchers here were actually able to figure out a way to directly optimize and align to human preferences without any explicit reward modeling or reinforcement learning. They posit that your language model is actually secretly a reward model in and of itself. So we can skip a few of these things using some super fun, fancy techniques. The way that this is actually able to be done is through a more specific looking data set of chosen, rejected, and prompts. So given one prompt, you have to have your both chosen and then rejected labeled outputs. These are usually going to be labeled by humans themselves. And through using this kind of data set, they're able to actually reformulate this preference learning into more of a classification problem that they're then using a very specific loss function to directly optimize this policy. Policy in this case being the actual weights of the language model. They're able to do this by actually passing in the prompt plus our chosen and the prompt plus our rejected responses, and then looking at the probabilities that are output for these responses from our language model directly. And so in using this, we can create this loss function to match human preferences by considering these relative probabilities of chosen versus rejected responses. The loss is then designed in such a way that as we actually increase the probabilities of generating based on the chosen prompts that we're showing and decreasing the rejected scores, we align more with our preference dataset. And so this is really the first way of doing this direct policy optimization, that you don't need any intermediate reward modeling or other complex reinforcement learning techniques. And as a plus, it was found to be a little bit more efficient and stable than the traditional reinforcement learning through human feedback approaches. And while that works pretty decently, this is generally applied after supervised fine-tuning is already done for this preference alignment. But other researchers have been taking this on and figured out that you might even be able to combine supervised fine-tuning and preference alignment all into one step. Which brings us to what's called odds ratio preference optimization, or ORPO. And the researchers that came up with this technique started looking more at the actual supervised fine-tuning stage and seeing where they could enhance it to also include preference alignment. The benefit of this then is that it really eliminates a total need for any reference or any reward model that RLHF and DPO relied on. And you can use just your single model to incorporate all of the preferences directly within the supervised fine-tuning stage. This then means that ORPO is considered monolithic in that it is a single stage training compared to the multiple different processes of reinforcement learning or direct preference optimization. And the way it works is it starts with the same dataset format that we saw for DPO, having your prompt and then labeled chosen and rejected. But the breakthrough actually comes with using what they call the odds ratio. So instead of the different probability ratios between a policy and reference model, we're actually eliminating the need for a reference model entirely by comparing the odds of chosen versus rejected outputs from our single model. To give a little side-by-side of the process of data through DPO and ORPO, we can see here that our preference data set goes through to both our policy model in DPO and then our reference model, which is the frozen weights of our original supervised fine-tuned model. We then create a probability ratio based on these, and then it gets put into the DPO loss. ORPO, on the other hand, uses just the single model. We calculate an odds ratio based on these chosen and rejected probabilities, and then they apply this with our ORPO loss, which is another specific loss function designed to do all of this, similar to how DPO had that. And the cool part here is that these odds ratios that we're calculating during training are weighted and added to the actual traditional supervised fine-tuning loss, something like negative log likelihood. And when we're looking at this, we can actually start to infer that ORPO is a little bit more similar to supervised fine-tuning, while DPO is more similar to reinforcement learning through human feedback. Essentially, while both of these techniques are trying to align the language model, the key philosophical difference here is that DPO is more of a let's solve the reinforcement learning problem more directly, whereas ORPO is more let's add preferences to supervised learning. And it turns out that ORPO is very effective. It dramatically simplifies preference learning by eliminating the need for any reference model and then combining supervised fine-tuning with preference optimization into a single training phase. This makes it significantly more efficient in terms of computation and memory usage than traditional DPO or RLHF approaches. As a plus, the researchers actually found that using odds ratios instead of probability ratios provides a more stable training dynamic and a better handling of these preferences, leading to more consistent and higher quality model outputs without requiring any of the complexity. So, for my more practical example of actually applying one of these techniques, that's why I went with ORPO. So let's get into actually applying this and doing ORPO with fine-tuning. And to really give this a fair shot and try it out, I wanted to do something kind of fun that would really demonstrate combining supervised fine-tuning and preference alignment very explicitly. So what we can actually do is do instruction tuning and preference alignment in one efficient training run. So to do this, I had to start with a base model, and I chose Llama 3.2 1B. This is a 1 billion parameter, super small language model coming out of Meta, and I thought this would be fun to just provide a small and easy example. And this base model is not the instruction tune model. So we're also going to be doing in this ORPO training stage, the instruction tuning of this base pre-trained model. So now with our candidate model chosen, what we need is a compatible data set. And what I'll be doing is using one of the best ORPO and DPO datasets out there, Maxime Lebon's ORPO DPO Mix 40K. This is a huge dataset of over 44,000 high-quality examples of chosen, rejected, and prompt combinations. It's specifically designed for ORPO or DPO training, and you can see the different sources that Maxime here has actually gone through and filtered out to create a more high-quality dataset. And so what we'll be doing is using this dataset, but actually a subset. So I'm going to be loading 15,000 examples and performing one epoch of ORPO training. This training with the small model is actually possible to do in a collab notebook. So I've got my notebook that I use to make the specific model linked here. So you can go through and see how I actually did the QLoRa config, loading the dataset, all of the different training configurations and runs, and then merging that LoRa fine-tuning with the base model and pushing it to the hub. Of course, I didn't come up with most of this code. A lot of this comes from Maxime Lebon's guide, where he actually walks through a little bit more of the specifics of ORPO training. I'll have this linked in the description below, so definitely check it out if you want to see more of the specifics of actually applying this training yourself to your own models. So after going through and running an ORPO training run across those 15,000 examples all once on Llama 3.2 1B, we can start to take a look at these specific training metrics to see if this actually all worked. Right now, we're looking at the probabilities of our rewards chosen versus our rewards rejected from the model. And what we're seeing here is that towards 1,000 steps, we see a clear trend of our model aligning towards the chosen responses and away from the rejected responses here in orange. What this shows is that the model is learning to assign higher probabilities to chosen responses when it generates and assign lower probabilities to the rejected responses from our training data set. Taking a look at our odds ratio, we can see that it's trending upwards here, which means that we're strengthening the relative likelihood of chosen responses, which will be on the top of the ratio, while reducing the likelihood of the rejected ones, which will be on the bottom of the ratio here. So good to see that upward trend too. Additionally, we can look at both our total loss and our traditional supervised fine-tuning negative log likelihood loss, and we don't see anything out of the ordinary. This shows a very healthy training dynamics with both losses decreasing initially and stabilizing around sort of our expected values. This indicates effective joint optimization of task learning and preference alignment here. One note is that in practice, it would actually be a little bit more effective to train this model on more data and additional epochs. But with these 15,000 examples and one epoch, we can already see that it's starting to effectively apply these ORPO ideas. So this leaves us now with our model, which I've just called ORPO Llama 3.2 1B15K. Nice lengthy name. And what we can do is actually try this out and see some metrics and just test it. Loading it back up in a collab notebook and testing if our actual instruction tuning has gone well. We can ask what is a language model here. And that was real quick. We got back that a language model is a machine learning model that can understand and generate natural language. And yep, this looks good. It generated a nice coherent response and then ended it in this instruction tune format. We know that this is actually working because if we load our base model, Llama 3.2 1B, and ask the same question, given that the pre-trained model is a completion model, it just keeps going and going and going and generating all sorts of text here in a not so coherent manner. But after our little bit of training, we could see here that it is effectively instruction tuned. And one thing worth noting as well is that while ORPO does combine supervised fine-tuning and preference alignment, it can still work on models that have already undergone some form of supervised fine-tuning. So you don't need to start with a more base language model like I actually did. But that being said, let's get some more understandings of how well our dataset actually did at improving our language model's abilities. So I ran through a few general benchmarks and comparing them back to the base model, we can see that our training actually decreased our AGI eval accuracy slightly and our MMLU accuracy slightly, but our ARC-C accuracy actually rose. And this is kind of cool to see given that the model was only trained on a subset of 15,000 examples for one epoch. It's likely that we would be able to push these a lot further with improvements and further training. Averaging up our first 4 evaluations of AGI eval, GPT-4All, Truthful QA, and Big Bench gives us a Noose benchmark of about 36.7%, which when comparing to some of the other language models that have undergone this Noose benchmark suite, we can see that that puts us a little bit towards the bottom, but not quite. Somewhere between this Code Quen 1.57b and Gemma Alpaca 2b here. But it's cool to see that a 1 billion parameter model that's only undergone a little bit of fine-tuning can actually score better with these standardized benchmarks, of course, on some of these averages. Better than some of the ones like the original Gemma 2b's, definitely, I suppose, the original Gemma 7b, and a few more of these models here. So even with our limited training and limited testing and a super small model, we can see that we were able to get some pretty decent results. Not bad. And with that being said, this concludes our overview of the actual alignment stage of training and getting the most out of your language models. I'll have links to additional resources so that you can read more of the specific papers, the guides, and all of the code that I use to actually create these models that we were showing here at the end from our practical application in the description below. And so if you like the video, please give it a like. If you enjoyed what you want to see and want to continue supporting the channel, consider subscribing, and I hope you have a great day. Thank you.